All right, so we're going to move on to 6.2. It's called Exponential Models. And really, it's just going to kind of continue with that exponential equation and adding in a little detail of messing with the time periods. Basically, not just every year, but sometimes doing things multiple times per year and compounded interest and this type of concepts throughout here. So the goal is I can write and analyze exponential models. So this means like for different scenarios and whatever you're given, you should be able to create a model or an equation that shows what's going on. And so you're going to see a pretty broad spectrum of stuff here. So the first problem is, it says, Juan is studying the exponential growth of bacteria cultures. Each is carefully controlled to maintain a specific growth rate. Copy and complete the table and find the number of cells in each culture. So there's 4 different cultures, A, B, C, and D. They each have the same starting amount of bacteria. The difference, though, is they're set up in ways where this one's going to grow 8% per day, 4%, or 2%, or 1%. But what they're going to do is they're going to grow them for different periods. Now, a lot of people see this, and you think like, okay, if it's going to grow by 8% for a day or 4% for 2 days, a lot of people see that and they think that that's going to be the exact same thing. So like, yeah, 8% over 1 day or 4% over 2 days, that's coming out to be 8% either way, or 2% over 4 days. So a lot of people look at this and think that these are all going to be equivalent. But in fact, they're actually not. So, and here's why. When you go to calculate these, let's use our kind of base equation we've been using. So if we have 10,000 and we do it times 1.08 for a single day, so to the first power, okay, it's 10,800. Now, if we do the same thing for this 4% one, so change it to 4% and do it for 2 days, you're going to notice that it's actually a little bit more. So it's 10,816. And the reason that it's a little bit more is that first day you get 4% added onto here. That means now going into day 2, you don't have 10,000 people anymore, or not 10,000 bacteria. You now have 10,400 bacteria, and that's going to get 4% added onto that, which is why you get a little extra added on each time. And so because of this, what you're going to notice is every time you do this, even though like the kind of like equivalent amount here seems equal, the more periods you do it for, you're going to get more and more and more. So same thing, if I switch this down to 2%, but I do it for 4 days. Whoops, I don't want to press graph, sorry. Come on, there we go. Again, so now 10,824, if we round down there. Cool. And obviously you probably see the trend now, but if we do it one more time for 1% for 8 full days. Yeah, pressed. What am I doing? Pressed graph again. Sorry. So we do that one, and now it's 828. And if you actually round up to 829. So again, hopefully that concept makes sense with you. Is the fact that this 1% gets added on, and then it gets 1% of that 1%, and then 1% of that previous number keeps going up and up and up by a little bit more every time, which is why each of these are subsequently more. Okay. So what's the relationship between daily growth rate and time, the time and the days for each culture? If you notice, they all basically multiply to be 8. We already kind of talked about that. And it says, would you expect a culture that had a growth rate of 0.5%, so kind of the next phase here, 0.5%, and you did it for 16 days, would you expect to have more or fewer? I would expect more. Okay. We could calculate if I had to guess. Obviously, it's not a linear trend because it went up like 16 and then 8 and then like 5. So, maybe it's going to go up like 3 or 4 here, but definitely going to continue to increase because of the same concept. Okay. All right. So with that said, let's jump to example 1. This says, in 2015, the population of a small town was 8,000 people. Population is increasing at a rate of 2.5% each year. Rewrite an exponential growth to find monthly growth rate. All right. So the yearly growth rate, we can do no problem. We've done this a few times now. We take our 8,000. We have 1.025 to the x. Okay. And that would be for a year. You could type in 1, 2, 3, 4 years, etc., and that would work. They want us to rewrite this to show monthly growth, though. We can't just divide it by 12, though, because, again, each month grows off the previous month, grows off the previous month. So to do this, we're actually going to do a little trick with this. So I'm going to take this equation, and I don't know, I keep doing that. I'm going to rewrite this x as 12x over 12. That's the same thing. Just throwing 12 over 12 in there is just like throwing a 1 in there. It doesn't change anything. And then I'm going to use my exponent rules, and I'm going to the reason I picked 12 is because there's 12 months in a year, if you're curious on that. I'm now going to regroup this a little bit. I'm going to take this 1/12 and I'm going to bring it onto the inside. So now I'm set up like so. And what I can do now is I can take this number and raise it to the 1/12 power. And that's going to give me what's the actual percentage for a single month. So I'm going to go ahead and do that real quick. To the 1/12. And so this right here is the actual, like the monthly percentage rate. It's actually, 0.205%. So if we do that, I'm going to write it here. Y equals 8,000 times 1.00206 to the 12x. And all I did here, these equations are the same exact thing. This is now just built for months, which is kind of cool. So now I can say, what's the percentage? So the question of write an exponential growth function, annual rate to model a town's population in years. That's what I did here. And then this is my monthly rate. So now I've got what this is asking for. So in a year, it's 2.5%. In a month, it's 0.206%. Okay. And they ask us to do the same kind of thing with this one. It says population in a small town is increasing annually. Actually, sorry, before we jump to that, let's go ahead and throw these in the calculator so you can actually see what I'm talking about. So the 8,000 times 1.025 to the x, that was our base normal equation. Then we have our 8,000, 1.00206 to the 12x. So if we go look at these, they are going to be pretty similar. The difference here is, so like they're equivalent, they're the same exact equation. If I drop that 12 off there and I put in that, now it changes it to months. If I take this 12 off my equation, I'll show you here. Now, when I put in 12 in this equation, it's going to be equivalent to one year in this equation. So if I look here, so there's that 1 year and it's 8,200. If I go down to 12, I'm going to see 8,200 here. So now this is a month by month breakdown of how many people are going to be there. 1, 2, 3, 4, 5, 6, 7, 8, so many months into it. So it allows you to modify things, allows you to create different equations based off what's going on. Okay. This says, what's the quarterly rate if you're increasing by 1.8%? So we take the same approach on this. We'd look at it and we'd say, let's say the population was 8,000. We have 1.018. And then instead of doing just to the x, quarterly means 4 times per year. I'm going to break it up to 4 over 4. So I'm going to take this number to the 1/4 power. And you'll notice that's pretty much the move. Like if you want to find what a specific fraction of times rate is, that's all you got to do. So if I'm going to put this number to the 1/4 power, 1.018 to the 1/4, there's our quarterly rate. So it's not quite a percent. It's 0.447% roughly. So 0.447% quarterly. Just like how up here we'd say this is 0.0206, or sorry, not 02, 0.2, my bad. Get rid of that dot. So 0.206% monthly. Okay, so that's how you can calculate based off not just yearly, but any other fraction of the year percentages. With this said, this brings into the concept of what's called compound interest. Many, many things, credit cards, banks, loans, etc., all operate on compound interest because they don't just throw the interest on once per year. They do it once per month or once per day, or sometimes what's called continuously, which we'll get to that eventually. So here's the formula for compound interest. P, which is your principal or your initial starting amount, 1 plus R over N. R is the interest rate, written as a decimal. N is your corresponding periods per year. So if you're doing it monthly, you're putting 12 here. And then T is your number of years. So if you were doing something monthly, you would put 12 here, 12 here, and then to the T. So this is a nicer formula. I was kind of just showing you a way to figure it out. This is the true formula that you're going to use whenever you're dealing with compound interest. So going forward, think of this formula. All right, so this right here, we got, I think that's Tamara, maybe. Invest $5,000 in an account with 4% annual interest. How much will there be after 3 years? And then it says, what if it's compounded annually, semi-annually, quarterly, or monthly? So if she's doing it annually, her formula will be, y equals the $5,000 she invested, 1 plus the interest rate written as a decimal, so 0.04, over. If it's annually, it's just one time period, once per year. So it'd be 1 and 1t. If she's doing it semi-annually, semi means half or twice per year. So that'd be the same everything except the ones would change to twos because she's doing twice per year, twice per year. And obviously you can just change this as she goes to then answer these. So, this one is going to be 5,000. 1 plus quarterly is 4 times per year, just like we talked about a second ago. So over 4 to the 4t. And then here, monthly is going to be 12. So 1 plus 0.04 over 12 to the 12t. Now, for all of these, they're asking you to do the same thing. Figure out what do they cost after 3 years. I'm going to go ahead and just enter those in. I'll type the first one in, but then I'll just pause it and do the others because you don't need to see that typed in a whole bunch of times. But if you're going to enter it in, just be careful with your parentheses and things like that. So if I'm doing this first one, I would enter it in like so, and I'm doing it to when t is 3. So 1 times 3 would be just the third power. So that would be her amount after just annually. So I'll write that down. I'll go ahead and get the other ones filled in as well. Okay, so there's the second one. Obviously, it's a little more. This is what you're going to notice. The more times it gets compounded, the more chances you have to apply interest, the more it's going to be. Okay, and here's the next one, 5, 6, 3, 4, 1, 3 if we round that up. So again, a little bit more money compounded quarterly. And then our last one, change this to a 12. And let's see, so this will be then 12 times 3, so 36. Okay, so that's going to be 5636.36. A lot of 3 6s there. Okay, so is it gigantic amounts of difference interest? No. Annually versus monthly resulted in $12 more on her $5,000 investment. But given the option, you would definitely rather have $12 than not having $12. So compounded interest, again, just like we saw in the earlier example and everything so far, you're going to see that it does, the more times you compound it, the more increase you're going to get overall. Okay, go ahead and read through this one and see if you can answer it. And then I'll go through it here in a sec. Okay, so I wrote my formula. $3,000 invested initially, 3% interest, monthly, so I used 12 and 12. So for 10 years, I already went ahead and plugged that in. That's, again, just plugging a 10 in right here. So the 12 times the 10 was 120. So 10 years later, $4,048.06. And then the last one says, how about 100 years? Oh, that's going to change. This is now going to be 1,200 because it's 100 times 12. And now we've got $60,031.45. So $60,031.45, which is pretty awesome. Like that you can turn $3,000 to $60,000. Granted, it takes 100 years. But you know what I always think about? Wouldn't it be really cool if like your great grandfather like did this and they left it in an account and said, hey, leave this to 5 generations down the road. Be pretty sick to just have like this sitting around that he set aside. Granted, you also got to account for things like inflation, that $3,000 100 years ago was probably more like $30,000 is now or something like that. So, maybe this isn't the greatest idea, but it would be really cool. So anyway, that's how compound interest works. Use your formula. Anytime we're talking compound interest, that's what you want to use.